Hi everyone, so we did our presentation on Laplace pressure, which is the pressure difference between the inside and the outside of a boundary that separates two fluids. For example, consider a drop of water. There is the pressure of the water on the inside and the pressure of air on the outside, and Laplace is the difference. Or, a bubble. We have internal and external pressure, with the boundary being the actual film of the bubble. Now, the Young-Laplace equation can be seen here, equation 1. So we have the difference of the two pressures, which gives us this equation, where gamma is surface tension and R1 and R2 are the radii of the curvature. So by that, we mean if you don't have a perfect sphere, then you take the long radii and the short radii, which you can see as A and B in the diagram. Now, consider a bubble and let's say it's perfectly spherical. This means both R1 and R2 will be equal. So our equation will end up just being gamma times 1 over R plus 1 over R. And this gives us the equation 2, but only for spheres. Looking at this equation, it's clear that pressure is inversely proportional to the radius. But this seems counterintuitive. If you think about it, it makes sense for the balloons to increase in pressure as they get bigger, right? We can test this out. To do this, we can try the two-balloon experiment. So our aim here is to see if pressure really does decrease as radius increases. We have two balloons, one blown up half full and the other about a quarter, and they're connected by a hollow tube. The neck of each balloon is closed off, so when we start, we'll just let go and see where the air flows. Here, our orange balloon on the left clearly has a smaller radius, and we want to see if it has a higher pressure. If it does, the air will flow from the orange balloon to the blue balloon to equalize the pressure. If the blue balloon has a higher pressure, the air should flow to the orange balloon, and they will both become equal in size, which is probably the more intuitive response. Here's our attempt.
As you can see, air flowed from the smaller orange balloon into the larger blue balloon. Watch again.
So we had a small orange balloon, as shown in the diagram, and the air went from the small orange balloon into the large blue balloon. So this shows that we did have higher pressure in the orange balloon, with a smaller radius, which agrees with equation 2. This diagram on the right shows the pressure-radius relationship of a balloon. So with the first breath, the pressure instantly increases, which makes sense because the first breath is always the hardest. And then, as you continue to blow up the balloon, it has less resistance because every bit of air you blow in has a greater surface area to spread the new force over, and since pressure is force over area, the pressure decreases. Now, obviously, as we get to near popping point, this won't be the case, as the latex of the balloon will reach its maximum stretch point, and then stress will be introduced into the material, and it will pop. But at low levels of inflation, here we have half and quarter full, we can take the tension to be almost constant, or negligibly different. So our balloons are roughly indicated by the two red dots on this diagram, which clearly show that the pressure is higher in the orange balloon.
For sources and further reading, please see below.